per iniziare praticamente l'apertura di questo seminario vorrei dare quindi la parola a John Halpin e spendere giusto qualche parola su chi è John Halpin. John Halpin già è stato, diciamo, partecipe nei nostri seminari, già è stato ospite nei seminari interdisciplinari, e lui praticamente è uno dei principali analisti mondiali del trasporto aereo. Infatti per diversi anni è stato anche professore associato alla Washington University di St. Louis. E nell'ultimo periodo dei suoi studi ha concentrato le sue osservazioni sull'analisi proprio delle evoluzioni green, soprattutto anche non solo in generale, ma dando un focus particolare proprio al settore campano. Quindi adesso lui aprirà il seminario con questa introduzione che poi verrà piano piano approfondita anche dagli altri relatori e dai seminari che seguiranno. Detto questo, Dr. Halpin is here. Can you hear me?
Yes, I can.
Okay. Well, can you start when you want?
Okay. Going into the presenter's view. It will be useful to look at a comparison of a concept of operations between a legacy turboprop and a battery-propelled propulsion flight system. To do this, I'm going to use sub-regional commuter cargo business case examples because these represent the simplest separation between the propulsion system and the basic airframe. To start, it's useful to go look at an example business operation. This chart is showing a cargo flight between Honolulu and the island of Maui. There's a subcontractor by the name of Commanda Air in Honolulu that works for FedEx, and Aloha Aircraft Company that has scheduled services that also carries parcel and cargo for FedEx. Looking at a flight between Honolulu and Maui, about 105 miles, moving a load which is a standard mail weight of 68 kilograms or 190 pounds. And what's interesting is, you know, when you come down to the shipping cost for the utility aircraft is 1/2 the cost of shipping it on a standard transport long-haul aircraft. The Kamaka Airline operates Cessna Grand Caravans. Aloha Airline operates the 737s. They're under different kind of operational requirements. We call Part 135 for commuter operations, Part 121 for scheduled operations. So there's a significant cost structure built into how you certify and how you operate the airplane. And it's advantageous for our technology to get started in Part 135 operations. To understand cargo operations, it's interesting to look at a sample fleet. On the left corner here, you see that FedEx, Amazon, most of the major cargo companies have a group of long-haul aircraft. Typical mileage is around, on the average, is around 1,600 to 2,000 miles. Near-term routes, typically serviced by the ATR, runs around 550 to 600 miles. Local feeder airlines, which are the commuter cargo types of aircraft, are typically around 150 miles for average stage length. This is the case we're going to look at because this is a practical application for the initial introduction of battery-powered aircraft. The interesting business case is that these feeder aircraft tend to operate within a 250-mile operating radius. Shown here is a distribution of many logistics centers for DLA, and the Amazon operating systems similar to the FedEx system. So this demonstrates that there is an established business case which we can look at for the application of these airplanes. In here, we see the beginning of the cargo feeder flight system in the United States. Starts around 1984. Shown right here is a Caravan, which was a passenger aircraft by Cessna in 1980. FedEx asked for an upgrade, which created the Cargo Master here, which was converted from a passenger to a cargo airplane. Shown next to it is the last mile transportation, usually in trucks. Recently, FedEx asked for an increase in size and capacity. They needed larger volume elements for carriage. They certified the Cargo Master last month here in the United States. And this is an interesting business case because this airplane precedes the launch into operation for the passenger version of that aircraft. Historically, passenger aircraft have been converted to cargo, but the cargo business today in local freight delivery has a stronger business impetus, and it is leading the introduction into the fleets. We're going to compare the energy disposition or consumption of a turboprop with a battery-powered system. It's important to remember some of the usages. Energy is what makes something work. Power is the rate of using energy. We need to be conversant in these two terms when we talk about batteries in comparison to normal fuel operation. Variations in operating systems from a CTOL, short takeoff landing, vertical takeoff landing, have different power demands as well as total energy requirements, which size the battery system. Shown in this chart is an example of the fuel consumption for the C-208, the Cessna airplane. It typically has about 335 gallons, 2,200 pounds, which is equivalent to about 5,800 kilowatt hours of energy. This is the fuel burn rate, and from this one can construct a series of mission legs, which are typical of their operation, which is in here. And so I'm going to have an example of a 145-mile mission leg. That consumes about 2,000. Well, that's we consume about 9,976 pounds, which is about 43% of the initial fuel weight. That weight of fuel has to be converted into battery capability, the kilowatt hours, and packaged into the airframe to replace the fuel system inside the airplane. The typical concept that's being evaluated today is based on automobile technology, where a group of battery cells are organized into modules. The modules are interconnected in parallel and in series to adjust the required voltage and amperage that's needed. The modules are linked together into the battery pack. The battery pack is encased within a metal structure usually. The purpose of the metal structure was twofold: to protect damage from occurring in the battery system, but primarily it was put in response to containing thermal runaways, potential fires, and emission of noxious chemicals in the passenger cabins of the airplane. This is an adaptation of that design by Airbus. It has evolved from the automobile industry, and Boeing switched to this when they went to the more electric airplane because they had battery fires in the airplane itself, and they had to have a way to isolate that. Controlling the temperature is a liquid plate here for thermal management, usually with a liquid cooling agent. All of this is controlled with a battery management system, which regulates power and heat and provides management functions for fuel, for the equivalent of fuel management that you would have in a fuel-based airplane. The operating envelope for the battery system is described here. On the right side is typical of what is used to describe the characteristics for the automobile industry. The chart shows here a decreasing line in here, which is to suggest that as the battery is used, it starts to have a decrease in the capacity of the battery, the storage capability of the battery. The line in here represents the operating range that is possible and is considered to be the state of charge. And this represents in here the typical operating range that one would expect to have. 80% value represents the 80% of the maximum charge of a new battery. And the practice today is to limit this because you start to damage the battery by migration of the lithium onto the surface of the anode and cathode. A film is formed similar to electroplating operations, which reduces the transmission or creates a resistance to the electron transfer and dissipates the energy as heat inside the battery. In the lower area in here, labeled as a grace period, are reserves for the VFR, IFR requirements, environmental control systems, vehicle management systems, and other flight management systems that you have in the airplane. There are several designs being advertised today where the associated subsystems in the airplane are not accounted for in the energy balance. The left side here suggests that parts of these requirements are derived from the characteristics of the battery itself, which are provided to the airplane person as a commodity item. There's a safe operating area defined in here, which is this white area over here, which has to do with the ability of the battery to withstand thermal conditions, high voltage conditions. And the point of this chart is these constraints have physical reasons. There's a lot of concern today that the regulators are over-constraining batteries. But as you look at the technical details, the capabilities of the batteries, the same flight requirements that we have for fuel-based airplanes, this chart represents that most of these constraints and guidelines are founded in established representable requirements for similar safety and similar production performance. A key element in this is the battery management system, which the OEM who designs and certifies the airplane will have to certify. It provides similar functions to the FADEC and the fuel management systems in our traditional airplanes. If we fly the mission that we were discussing, about 145 miles, with a traditional turboprop airplane, when we arrive at a destination, we will probably refuel that airplane That airplane will land with about 15% of its capacity unused. That is the reserves that are normally required. It is topped off for the next mission leg, normally just the amount that's required for the next mission leg. For the battery, the topping off or the recharging occurs with electrical charging stations. The turn time between stops in the mission is a function of the charging time limited by the charging rate. Here, the battery capacity is divided by the charging power of the charger. The battery capacity in this sense means how much energy do you need to go to the next leg in the mission. Charging power is the rate at which you can transfer the charge from the charging station into the battery. The 0.9 represents the decay in the capacity of the battery as the resistance films are formed. What this means is that 10% of the energy that leaves the charging station is dissipated by heat inside the battery and represents a loss or an additional cost for the fuel. Today, we have had an evolution of charger capabilities from about 125 amps to a limited amount of kilowatts up to a rapid DC fast charging station technology, which is just coming on stream today at about 900 kilowatts. These systems are starting to be used in advanced sports cars. This is a German sports car, high-end car. It's being used as in the Alice e-cargo airplane that is being sponsored by DHL cargo freight support. As the battery is being recharged, two parts of degradation are occurring, or loss or change in capacity is a better way to present it. As the battery sits stationary at a fixed temperature, there is a continuing chemical process taking place inside the battery. This is the film formation that we discussed in here. These are the temperatures of the storage, and this is typical data for lithium-based batteries in here. This represents total time in years, which represents in here, if you sit at a very high temperature, you have a relatively rapid loss in the rate. However, in most cases, the practical hot time reduction is about 10 to 15%. And that's part of this curve here. Second thing that occurs as we go through a recharging cycle. Let's say we start with 80% capacity, we reduce it, consume down to 20%, and then we recharge it back to 80%. That represents one of these curves in here, which is the magnitude of that cycle and the number of times of occurrence before it reaches about a loss of 20% or so in the capacity of the airplane. This process is very similar to low cycle thermal fatigue that we see in the hot sections of the turboprop airplane or of our normal jet engine technology. It's a well-established practice. Shown here is an application that we would accommodate this by a cumulative damage analysis process to estimate the operational life before we would have a replacement requirement for the battery pack. Let's go back now to that chart we had for the fuel consumption for the Cessna airplane. We're going to go fly a 145-mile mission. We start at a fixed operating base. We go to the destination. The airplane is then parked. It is being unloaded and reloaded. During this time, it is being recharged. This is the degree of charge available after about a 2-hour, after about a 2-hour turn. And so we can recover about 70% of the equivalent energy to continue the next leg of the flight. It's returning back to the fixed operating base where the cargo hub is located. It goes through the same process. It sits on the ground for about 2 hours. It reaches about 65% capacity in terms of stored energy. It goes through a third cycle, and it's at the fixed operating base at the end of the operating day, which then can recharge to 80% with a slow charge, which is typical of how you would charge your electrical automobile. This represents the pilot's duty day, which is one of the constraints on how you operate an airplane. And this cycle is just about compatible with about a 12-hour duty day for the pilot. The duty day encompasses how much downtime the pilot has plus direct flying hours. Estimate the life in here. We have about 3 cycles a day, representing a 29% charge for delta charge for consumption and recharging. This charge level here is about 62%. These represent the number of times that occurs in a day. This is the cycle for a year count. This is the life capacity that's expected for this level of cycle charge discharge. So this is 10,000 operating hours. This is 6,700 operating hours. This number divided by this number says that in a year you use this fraction of your life capacity. Summing these two together is the life capacity consumed by the cycling is about 12%. But there's an additional 10% loss in thermal aging. So this suggests that the expected capacity and capability, the replacement time will be about 7.7 years. That is equivalent to about 5,600 or so operating hours. The other operating concept would be, and this is one of the assumptions in a lot of the sizing of some of the e-vehicles today, is that we would leave the hub, go to an intermediate stop, have a term time of about 2 hours for the cargo exchange and other operations, and we would return now to the hub. Now, in a sense, this is doable, but as you look at this charge, we are down to 15% of the capacity that we started the working day here. So this is a somewhat marginal concept of operation, but it depends on the size of the battery. If we have extra capacity in the battery, these changes will be smaller. Here we went from a fixed operating base hub, return to the fixed operating base with no topping off. It takes about 5 hours to recover the 80% requirement. So we can go through the second mission for the day here. These are multiple 68% discharge recharge cycles, occurs twice a day here. Assumes this fraction of the life per operating year reduced by 10%, and that reduces the expected operating life before we have to replace the battery system, the battery pack system, to about 5 years and 3,800 hours. Now, the business implication of this is illustrated here. What we have is a chart which shows the typical maintenance cost and cycle for the engine typical of this class of airplanes and the Cessna airplane. What you see here, the first two things is that the airframe average operating cost per hour is about $26. For the engine is about 23. So that says it's about evenly split. For the engine, the hot section of the engine normally undergoes an inspection around 900 hours. For the PT-6A. It's been extended to 1,800 hours. The engine overhaul time is about 3,600 hours. The cost shown here is through a contract arrangement called Power by the Hour certification by the engine manufacturers. In addition, there's some unscheduled maintenance that occurs in the airframe and the engine system. This becomes then an estimate of the maintenance cost. So a comparison of the technology from a business point of view looks at this chart and recognizes that the electrical system, battery propulsion system managed with a topping off capability with advanced recharge stations provides 5,600 operating hours, which exceeds the maximum limiting hours for the major engine overhaul rate, which is 3,600. Now, this is not an arbitrary number because this engine has been in service for over 30 years, well-known, well-established life limits and well-established costs. So this becomes then the basis of the estimate that electrical propulsion, battery propulsion, can reduce the operating costs of the electrically powered airplane by about 20%. That comes predominantly from the engine, not from the, there is no change in the airframe. I need to accelerate. This chart represents the emergence of the current state of the batteries. We expect to have a capability by 2025 full rate production of about 325 kilogram or watt hours per kilogram. That capability would allow the equivalent airplane to the Cessna to operate in these circles here, different locations shown for here. That's similar to what I showed for the United States. This chart here shows the expected delivery rates. In here, this is projected here as cumulative deliveries on the right. But these are not real deliveries. These represents letter of intent. That there's a deposit made to encourage the manufacturer, but there's only about 500 firm contracts out of that 9,000. This chart here represents the expected investment it takes to get an operating system. The Lilium is about 3,500 here, but they've extended the certification time by 1 to 2 years. Current estimate is it will take $4 to $5 million US dollars to reach a conforming prototype to start serial production. These letters of intent, memorandum of understandings are conditional. There's usually a requirement for an operational utility evaluation test. This chart outlines several examples of where this is actually happening today. I'll cite particularly an example in the Orkney Islands. There's a home fixed operating base here for Long Air, which operates through these series of islands dominated here. Typically, they would leave the fixed base, maybe go here, and return. And so they would have 2 to 3 stops. Interestingly, these stops at the outreached islands here are 7 to 10 minutes. At the fixed base, it's about 30 minutes. There's a break in midday for about 3 hours. That allows them to have 21 missions per day to provide revenue for income for the operator to pay for the purchase of the airplane. 21 missions per day is interesting because that's also the guide for the goal, business goal for the urban air mobility activities that are proposed for not VSTOL, but for vertical takeoff and landing operations. So this represents the challenge then from a business perspective of e-propulsion versus the fuel-based terminal prop systems. TIPSTOL has certified vehicle with the methodology we have sort of outlined, but the constraints have done this successfully. That's created interest by Textron, who has just acquired PIPSTOL. This chart suggests that there's going to be an induction period of about 10 years while the operating concepts are demonstrated and agreed to. And then we will see a serial production beginning in the early 2030 timeframe. In conclusion, we are going to see a turnover in the aircraft fleet, not only generated by environmental concerns, but there's been a major increase in e-commerce. That is driving a revolution in the change of the large-scale aviation fleet. The recent events over the last 5 years is leading to a restructuring of the just-in-time supply chain. There's a restructuring to focus more from a global to a regional focus. This means more sub-regional computer cargo vehicles will be produced. Escalating fuel prices are also driving this concern, and government mandates to improve energy independence. You see this locally in the passenger to freighting conversion, where at Capitano, the ATR has started a business function to do this in response to these pressures above. Short range, 200, 250 sub-regional mile cargo and commuter systems are expected to be the leading transformation. They're expected to be that because they have a well-defined technology, they have a mature database, and the operational structure is understood. That's why we went through this concept here. To demonstrate, at least from a U.S. perspective, Textron is purchasing TIPSTOL because they view that as a company that has properly integrated the changes in the concept of operation for the vehicle to make it compatible with the business structure needs of the community. I expect we will have a new modified aerospace ecosystem, which recognizes that some of the changes we have to make in our current time system are valid and profitable for the operators. I'm pleased to have this opportunity to talk with you. I'm interested in how will we respond to these challenges and changes. Thank you for your attention.
Thanks for your time. Thanks for your time, Dr. John, and the presentation. Okay. Okay. In English. Okay. Ok. La presentazione del dottor John apre diversi spunti di approfondimento. Voglio ricordare un attimo che per coloro soprattutto da casa, che se hanno delle domande, eccetera, c'è un form che praticamente uno può compilare con la propria domanda e indicare a quale relatore è rivolta. Detto questo,